you may find out right now we have the basic skills to construct the surface model of the 3D object anyway. You can do that through the isosurface. You can use the patch for the display. And most importantly, if you are dealing with an isotropic image fallon, you can use the code that are provided to you, the isotropic fallon, to correct this kind of issue, right? So what would be the remaining issues? That would be, can I create a much beautiful model that is really suitable for the 3D printing? Okay, that would be the issue. So for the second part, I'm going to address this issue by using several different post-processing steps right here. So in the second part, I'm going to take this dental CT imaging as the example. Actually, this is the file. This is a file for the two groups that I asked you to perform the dental CT. Anyway, this is exactly the same file, okay? So again, we will load this made file into the workspace. You can again display one of the slides is exactly like the left-hand side image right here. And also, we can reconstruct the surface model on the right-hand side. This is what we are going to do, okay? So now, again, we're seeing the MI materials underline L12. You should be able to find another M file named as the dental underline model.m. Okay, so let me do it now. You should be able to find this one. Dental underline model.m file. Okay, you should be able to find this one. So let me close the figures. Let me open it. Okay, the dental one. Okay. So basically, you may find out within the content, there are so many different codes, around the 72 lines right here. But you may find out that I actually separate all the codes into different sections right here. So let's just start by the very first section. You can see I load. There's a data set called dental underline data.met file. Okay, I load it. So let me do it now. If you only want to run a specific section, please do not click on this run button. What you can do, you can click on, you can press the control with the enter. Or maybe you can take a look right here. This one, run section. You can see the hotkey is the control with the enter. So this is the way that you want to actually run through the whole file. You will simply run through this section. Okay, so it won't waste all of your time because you don't need to go through all the content, right? You can simply go through the very first section. So just remember this hotkey, control with the enter. So you can see I just run the very first section right here. Now you can see the imaging size is 378 by 378 by 154 right here. Okay, so again, you can see the image resolution. This is again not isotropic. This is anisotropic fallon. So you can see the in-plane resolution is more like 0.36 millimeter by 0.36 millimeter. However, for the slide thickness, you can see it's almost twice of this 0.36, right? You can see the value is 0.75 millimeter. So again, you need to correct this issue. So you can see for the line number 5 right here, I again use the isotropic fallon, okay, this function. But now you may find out a little bit different for the final input right here. I switch the input of the mean to the mean. It's pretty similar, right? MIN minima, MEAN average, okay? So this is something that you can change. When you are using the MIN, that means I'd like to adjust. I'd like to change the factor size into the minimal value of these 3 values right here. But if I'm using the MEAN, that means the average value of these 3 numbers. I think there are 2 different ways that you can adjust the factor size right here. But anyway, you can go for either one, MIN or MEAN, both are fine, okay? So you can see this is the imaging that I have already corrected for the issue of the anisotropic fallen. So it should be this size, okay? So then we can go for the test number 1. I think the test number 1 would simply be what we did before. You can see I directly send this IMG, this image fallen, into the ISO surface, right? And now you can see the ISO value is 1,800. Again, you need to check, you need to find out the best ISO value by yourself, okay? I've already introduced how to do that, but you need to identify this value by yourself. You may try several different ISO values to determine which surface is most suitable for the 3D printing. You need to try it, okay? Then you can see the figure, the patch, the lightning, cam light, and you can see for this example, I actually put 2 cam light because I think the one light is not light enough. It's good enough. It's not good enough. So I actually put 2 cam light. Okay, you can do that. Okay, and this is a view angle. Okay, so the only difference right here would be this one. You may see that not only vigor, I actually use vigor with some setup right here. I change the color of the vigor. What is the color of the vigor? This is the background. You can see the final 3D model would come with the dark background, right? So this is a color. You can see the color 0, 0, 0 means no color, right? That is the black. So let me run this part first. Again, you can use the hotkey like the Control with Enter, or maybe you can press this button, run section right here. You can do it either way. So again, because now this dental CT is a little bit large, so it will take several seconds to several minutes. So you need to wait. So every single time when you see the busy, you see this kind of the message right here. That means your variable is doing something. Of course, you can also check this through your task manager. You can see whether your computer is doing something now. You can see the CPU is actually occupied by MATLAB. You can just check it. I may find my MATLAB right here. You can see, okay, not too much. So all you need to do is just wait, okay? You need to wait. I think it is done, okay? Once it is done, you should be able to see this model. So again, I want to emphasize now the background is fully black, right? Because I just changed the property of the color to 0, 0, 0. That means black. Again, now you can just click on this rotate 3D icon, and now you can rotate it. So what you did right now is you actually reconstruct the surface of this dental CT data right here. And you may find out, yes, I am able to see a lot of different things. For example, the cervical spine. Let me move it. This is the cervical spine, C1, C2 right here. You can see the base of the skull, okay? You can see the teeth and the jaw right here, right? You can also see the nostril, a little bit leg, because this is a very, very huge surface model. Okay, so you can see this is the hole that the spine can actually go through this. So anyway, I know lots of you didn't learn the anatomy right now, but anyway, once you have the chance, you will appreciate that how we can see, how we can observe the anatomy through this kind of a medical imaging. Okay. So right now, I just want to ask you to run this section. It may take several times on your computer, but please just run for this first and the second section, and make sure that you can also see this kind of the results. Okay, just do it now. Just do it now. So once you did it, just tell me, is this model is pretty enough, good enough? To me, I have to say this is not good enough. You can see the surface is not smooth, right? Okay, so we definitely need to do something to improve the quality. Okay, but anyway, just try to observe this kind of 3D model by yourself right now. Okay, so let's continue. So let me take the control back. So now you can see, because the very first one, we just go for what we did before, but the result can be less than ideal, right? It is not good enough. So for the second part, you can see the test number 2, start from the line 21st right here, okay, 21 right here. You can see the test number 2. I just try to put the note right here. I'm going to do so-called image smoothing because I really want the surface to be much more smooth, right? So what I can do right here, you can see for the command line 22 right here, I just try to use a method function named as smooth3. Okay, so I think it's pretty intuitive. Why smooth3? 3 represents 3-dimensional. So actually you can do so-called image smoothing in a 3-dimensional way. So this is the function. Of course, you can help for it. But now you can see the very first input would be img. Of course, this is our image file, right? But the second and the third input, again, this is kind of the pair input. So you need to control the box. It's pretty like what? It's pretty like the convolution kernel. If you may recall, we can control the kernel, right? What we did for the convolution, if the kernel size becomes larger, that means you will get a stronger smooth result. If you use a very small kernel size, that means you will have a very little effect for the image smoothing because you only consider the neighboring voxels within. For example, in this case, 3 by 3 by 3. I only consider the voxel close to me. But if I set the box size to, for example, 10 by 10 by 10, then you will have a very huge effect for the image smoothing. Of course, we can try it. We can try it later. But right now, what I'm going to do, I'm going to simply run this section. Okay, only this section. So just wait a couple minutes. So you can see the output for the smooth number, smooth 3 right here. I just create another variable named as the image2. Okay, so you need to remember for the command line 24 right here, the very first input, you should replace the imaging by image2 because now image2 is the output of the smooth 3. So if you only put the img right here, that means you are not using the smooth function right here. So now you can see, I try to give you the results. For the left-hand side, this is the imaging that I just produced using the smooth 3, right? This is the imaging, the original imaging. So now you can easily observe the surface. The surface, this is much more coarse, right? This is a smooth one, a little bit different, right? So I think I did prepare the slides for you right here. You can try to display the imaging. You can take a look for the left-hand side. This is the original image. For the middle image right here, I applied the box size of the 3 by 3 by 3. So you can see the effect of the smoothness. The final one, I increased the size to 5 by 5 by 5. So you may find out, of course, when you are increasing the box size, the smooth effect would be stronger. However, you don't want it to be that stronger. Sometimes over smooth will cause the loss of the information, right? So you can try it again. This is the parameters that you can try. Which kind of the parameter can give you the ideal result that you think it would be the most suitable condition for the 3D printing? You can think about this, okay? So feel free to try it. I can try to make a crazy one for you. For example, I can try to create something like, it's definitely too big. Anyway, 9 by 9 by 9, okay? Let me try it. Let's see what would happen, okay? Just wait for a couple seconds. You will see the results. Okay, so now you can see this is the result. This is the result generated by a box size like 9 by 9 by 9. So now you can compare. This is the result generated by the box of the 3 by 3 by 3, right? And this is the one generated by 9 by 9 by 9. So now you may see, wow, the surface right now is broken because you lost too much information, right? Over smooth can cause this kind of the tragedy, I have to say. I mean, the broken surface is not good enough. So if you send this kind of a model for the 3D printing, it will be really, really terrible. I mean, your score will be really, really terrible. So don't do this, okay? So anyway, you need to try it to identify what is the best setup for this kind of a process, okay? So let me change the value back. I just want a 3 by 3 by 3 in this case, okay? But I just want to emphasize for different model set, you may apply different parameters. You cannot always use the same setup based on my example. You should not do that, okay? So again, I'm going to give the control back to you. Please try this section. Try to observe the effect of the image smooth right here. So basically, you should understand that when you are using the smooth 3 function, it's actually doing something pretty like the convolution. You are doing something directly on the image. Okay, so this is so-called smooth 3. Okay, so let's continue. I don't want to delay your time. So let's continue. So of course, some of you may think these results is good enough. But I have to say, you still have several different options to improve the smoothness of the surface. So what I'm going to introduce for the next section, you can see the test number 3 right here. Not only the image smoothing, I'm going to add something like the mesh smoothing. So what is mesh smoothing? I have to say, not only the imaging itself, that you can perform the imaging smoothing. Think about this. Can I perform the smoothing directly on the vertex coordination? For example, I can just try to put the 2 vertices closest to, much more closer to each other. That is so-called mesh smoothing, right? We can also do that. But I have to say, in order to do this, you need to make sure that you have this function, mesh smooth function. Okay, again, this is the function that I created. This is not the built-in function for the MATLAB. However, if you want to use this mesh smooth function, you can see this is actually included in the today's folder, right? If you want to use this mesh smooth function, please make sure that you also have this subfolder, toolbox underline graph. So basically, I used some functions provided by other toolbox. This is not the built-in toolbox included in the MATLAB. So if you really want to use this mesh smooth function, you need to make sure this subfolder is also included in the current directory. Okay, this is very important. If you don't have this subfolder, you cannot perform so-called mesh smoothing. Okay. So now you can take a look. Not only the smooth 3, of course, for the imaging smoothing. Now you can see for the line 41, I do have another one called the mesh smooth. But what is the difference between these two things? Not only the principles, but also the timing that you can use this. Think about this. Smooth 3, because you are doing something directly on the imaging volume. So if you do have the IMG, you can do something right here, right? But mesh smooth, if you want to use this, you definitely need to get the face and the vertices data on hand first. Because you are doing the mesh smoothing, right? Mesh means the face and the vertices. So you need to get the F and V first, right? You need to get the F and V first. So you can only perform this kind of mesh smooth after iso surface, okay? So you may find out you need to perform the iso surface first, so you can have the F and V. Then you can input them into this mesh smooth function. And you may find out the output function will only be V, because I don't need to adjust the face. All I need to adjust is the location, the coordination of the vertices, right? So all I need to do is I can modify the value of the V and output it again. So you may find out for the rest of the part, this part would be identical to the previous one. But the only difference is this vertices variable, V, is modified by this function, okay? Okay, so now you can see the results right here. Of course, you can again make the comparison. Supposedly, it would be smoother compared to the previous one because now not only the image is smoothing, for the right hand side now you also have the mesh smoothing. So take a look right here. The left hand side you only have the 3D image smoothing. The right hand side you have both image smoothing and the mesh smoothing. So maybe I can enlarge this for you so you can make the comparison easier. Just focus on this part, you can easily see the difference, okay? So again, I just want to emphasize that you need to include this folder, the toolbox underline graph in the current directory, then you can perform this kind of the mesh smooth. If you didn't have this kind of the mesh smooth function, and you didn't have this subfolder, it will be no way for you to perform this kind of the mesh smoothing, okay? So you need both of the files and the folders right here. Okay, let me finish the final part and then you can discuss with your group member. So the final part is the test number 4. Okay, test 4 right here. Now you can see not only the imaging smoothing, you can see the mesh smoothing right here, right? But in between, I actually add one more thing called reduce pitch. Reduce pitch. Let me take this example right here. You can take a look right here. What does reduce pitch represent? What does the reduce pitch mean? Take a look right here. For the current examples on the screen, you can see the left-hand side is so-called full patch. Full patch means you have all the faces. You have all the vertices right here. But for this case, actually, the image is pretty large, right? So you can take a look right here. How many faces do I have? I don't know how to say this number. It's around 1 million, right? 1 million right here. And for the vertices right here, you can see 763,000 vertices right here. So actually, the mesh, the content of the vertices and the faces are pretty huge, right? So you can see this kind of the data would result in this kind of the so-called full patch. So dense, so complicated right here, right? So if you really want your surface become a little bit smooth, another way you can do is you can reduce the pitch. You don't need so many vertices. You don't need so many faces because that means too much details. You don't need that much detail, right? So what you can do in the middle of the example, you can see this is the result from the reduced patch to 50%. Okay, I reduced the patch to be the half of the original size. Now you can see the space between the edges or the area of the faces actually pretty different compared to the original one, right? For the right-hand side, you can see if I reduce the patch to 10% of the original sizes, now you can see everything become much more clear. You can actually see a lot of the faces right here. So for a face that if you use so many faces or vertices right here, it will give you too much information or too much detail. That means it may also contain too much noise within. So if you want to, again, improve the surface, you can also use a reduced patch. For example, reduce the patch to 50% or 10% right here. So you can see the code for test 4 section right here. You can see code line number 59 right here. I use the reduced patch. Again, if you want to use the reduced patch, you need to have the F and the V on hand first. So you can only perform the reduced patch after the ISO surface. Okay, so you can see you need to input the F, you need to input the V, and the third input would be the percentage. or be the factor that you'd like to reduce. So 0.1 means you want to reduce the size to 10%. Okay, 10%. So if the value, it should be between 0 to 1, right? 1 means nothing changed. 0 means nothing left. You don't want this one. So I think the value between 0.1 to 0.5 would be ideal. But again, you need to try it. You need to try it to find out what is the best result, or which one will give you the best result. Okay, so let me again run this section, and you can do this too. Okay, so the only difference is the command line 59. But again, you need to wait. You need to wait for the process of the reduce page. So anyway, if you add more functions into the section, you definitely need to wait for a longer time. But anyway, now you can see this is the result. If I reduce the page size to 10%, what will it look like? So now, again, on the right-hand side, it is the reduced page. On the left-hand side, this is, I think, only the image is smooth right here. Let me compare to the original one. So this is the very first image, the original image right here. So now you can see the effect. I have to emphasize that I'm not saying the details is not good. I'm only telling you that if you are going to do the 3D printing, sometimes too much detail won't give you a good result because the surface would be too coarse, would be too complicated. So what you need to do is reduce the page size. This is what you can do. So of course, you can find all the codes within this dental underline model.met file, .m file. So this is a quick comparison for your reference. You can see the result from the test 1, 2, 3, and 4. I think it could be very easy to see what is the difference right here. Okay, again, oversimplified the model may be not ideal. Okay, so you need to find out, you need to just tune the parameters to find out the best result. Okay. So finally, homework. But again, today we don't have the homework. Actually, the homework is a team project. What I'm asking to do right now, please download the project file from my website, and you can try it. Whether you can use the code that you learned from today, apply it to your project file to check whether you can actually create a 3D model or something. But again, I have to say, the details for the detailed information, the detailed instruction for all the groups will be mentioned for next week. Okay, but today I just want you to make a quick test on your model file. Okay. Anyway, so try it whether you can construct any 3D surface model by yourself. Okay.